Geology. So please give Dave Leroux a big welcome from Ollie.
Can you hear me? Yes. All right. So first of all, hi everybody. This is not the class that we're going to be talking about. I'm really sorry. Let's see. How do I do this? I should have practiced this, Marge. That one? No. Yeah. No. No. Okay. Down. All right. Starting in class with a lie. The bizarre geologic history of Orange County. That's not the name of the class. So here we can see comforting lies versus unpleasant truths. Okay, this is the real name of the class. The amazing, incredible, unbelievable geologic history of the Newport Beach and Southern California areas. All right, and I was trying to mimic sort of a Tom Wolfian approach. But you know what? You know what they nailed me on? I occupied too much space. It was like too many superlatives, so I had to shorten it. So here's another picture. I taught this a couple of times at the Oasis Senior Center, and now we're at Ollie, of course. All of these pictures, except for me levitating rocks, you will see. You'll see Corona del Mar, Crystal Cove, how to cook a chicken. You will learn the importance of how to cook a chicken and how it ties into geology. No lie. Corona del Mar, the chalk cliffs of Newport Beach. Did you know that there's chalk cliffs in Newport Beach? Dover. All right, like Dover. And then we'll look at this in detail. All right, that's what the class is about. Okay, who the heck am I? Marge told you a little bit about me. So I got a bachelor's at USC. I did my PhD at Northwestern in stratigraphy, layers of rocks. I was an assistant professor. That's what I call myself what's the word I'm looking for? I was an assistant professor at Stanford. I didn't get tenure, so I went to the University of Puerto Rico, and then I went to the oil industry for like 25 years. So here's a little thing. This is from Calvin and that's Calvin, right? Yeah. Let's start at the beginning. When you add something, you increase what you have. I don't want to learn this. It's completely irrelevant to my life. This isn't irrelevant. Everybody needs to know about addition. I don't. I can get along fine without math. Oh, yeah. What do you do when you grow up? Everybody requires some math. That's not all true. I'll be a geologist. That's not really a job. All right. These are places I've done geology in my career. Again, I was in the University of Puerto Rico for a number of years, and I've been to like 23 islands. I worked Bakersfield area for 15 years for Chevron, and I've worked, Asia and Australia. Mostly in Australia. I was working Papua and New Guinea, but I've been to Australia a couple of times. Anyway, so I've seen a lot of rocks. Class structure. Most of the time when you learn something new, like if we were doing French, we'd say, la plume de ma tante est sous la table. You start off really basic, right? So we're not going to do basics. We're going to go right into high gear, and I'm going to talk to you like you're research scientists, but I'm going to explain everything. So there's no baby stuff in this class. This is all hardcore stuff. Okay, so we're going to dive into the meat, right? All right, okay. Now, obviously, I don't want to go over your head, so you can ask questions, and I'll try to explain myself clearly. I'm also passionate about geology, as Marge said, so I tend to stray off on things that interest me. So I'm forewarning you, and to be forewarned is to be like this guy. All right, so here's the 4 lectures that you're going to hear. The first one is on the plate tectonics of Newport Beach and the world, rocks in Newport Beach, and earthquakes in Newport Beach. And again, this is not really just Newport Beach, but the whole area. And then the ice ages in Newport Beach. What was it like during the ice ages here on the coastline? Okay, now in plate tectonics of Newport Beach, again, I'm talking about the amazing, incredible, unbelievable geologic history of this area. So I'm going to talk about what's normal in plate tectonics and why what's happening here in Newport Beach or Irvine or wherever is not normal. So I'm going to start off talking about normal plate tectonics, and then we'll talk about weird plate tectonics like that's happening here. All right? And we're going to incrementally walk up to this so you won't get lost. Okay, again, this is Little Corona Beach. The rocks are so cool that I'm going to talk about. This is obviously Dana Point, that people actually go there to get married because of the rocks. They're just so traumatic. Nobody believes me. All right. Okay, now since this is a beginning class, I'm going to do a little bit of review. So I apologize. Everybody know the 3 types of rocks? Okay. So the thing is, you can go to the internet and you type in, what are the 3 types of rocks? And that can get you into trouble. Here's a young lady type, name the 3 types of rock, and it's classic, punk, and hard rock. So the 3 types of rocks are called igneous, sedimentary, and metamorphic. All right? We need to know that for the class. And what that means is that igneous rock is usually the one we start off with. If you have a molten rock, molten magma, and you crystallize it, it becomes an igneous rock. So any igneous rock is formed from the cooling of molten magma. If a stream cuts through an igneous rock, like through a volcano or something like that, and erodes the little pieces of a rock and makes sand out of it, and that sand gets glued together, it becomes a sedimentary rock. So this is a sandstone, so it's made of sediments that came from some other rock. And then if you bury and squeeze the rock until it changes the mineralogic crystals in the rock, you get what's called a metamorphic rock. All right, so igneous rocks come from molten rock. Sedimentary rocks come from the erosion of other types of rocks and then gluing together by cementation and compaction. And then metamorphic rocks are recrystallized igneous and sedimentary rocks. All right, so here's examples of rock types. A granite. We've all heard of granites. Granites and diorites are sort of like in an extended family. There's a whole bunch of different types of rocks similar to granites and diorites. And then basalts. You're going to hear a lot about basalts in this class. Obsidian. Obsidian's is one that everybody always shows you, and I don't think I've ever seen it geologically. I mean, it's a weird rock type. It's glass, essentially. Okay, and then those are your igneous rocks up here. The big ones are, again, basalt and this granite and diorite family. Sedimentary rocks, this is a rock made out of pebbles. So it's called a conglomerate. It's just a rock made out of pebbles. Sandstone is a rock made out of sand. Shale, you think, what's shale made out of? It's a rock made out of mudstone. Shale is a mudstone. Limestone and dolomite are basically sedimentary rocks made out of broken down fossils and things like that. So if you go to the Florida Keys, you'll see the sands there, if you look at them in detail, are all little micro pieces of, coral and algae and corals and so forth. Metamorphic rocks, remember, are recrystallized rocks. So a slate is just a recrystallized shale. It's the same thing, only the minerals have changed in it. A schist is basically a slate that's been a little bit more metamorphosed or heated, and it's turned into a bunch of mica. Serpentine we can skip. Quartzite is basically just a metamorphosed sandstone. Marble is basically a metamorphosed limestone or dolomite. So it's a recrystallized limestone or dolomite. And then a gneiss, which is basically a metamorphosed granite or diorite. Right, so those are basic types of rocks. Rock jokes. I took that for granite. We're going to go through the basic humor in geology. My sediments exactly for sedimentary rocks. You look nice. You don't know schist. All right. Now you're thinking to yourself, those are such stupid jokes, right? Right? No one would ever take those and do anything with them, would they? Oceanic arc stratigraphy in the Caribbean, don't take it for granted. By lithic volcanic sandstones derived from oceanic crust in the Franciscan complex, sedimental memories. Lead author. This turns out making funny titles of papers doesn't help you climb a career path. Okay, so volcanic rocks are formed from volcanoes. So you have molten magma and it freezes and you form a volcanic rock. This is from Yosemite. If you take the same volcanic rock and you freeze it more slowly, you get bigger crystals, and those are the crystals that you'd see on the flanks of the walls at Yosemite. This would be a metamorphosed rock where you can see some layers, but it's all been recrystallized. And of course, the beautiful rocks in the Grand Canyon are all sedimentary rocks. This is what I specialized in. All right, again, if you go and you just type in the word rock cycle into the internet, you might end up with this saying that we go from the 20s rebellion jazz to the swing dance. That's the rock cycle. That's not what we're doing here. The rock cycle means how all these different these rock types are related. So a magmatic rock, so a magma is, molten rock. If it cools, it becomes an igneous rock. If the igneous rock melts, it becomes magma. If a metamorphic rock melts, it becomes magma. If a metamorphic rock weathers and erodes by streams and frost and so forth, it would become sediment. If the sediment becomes compacted and cemented, it becomes a sedimentary rock. So you can go from one rock type to another. They're all interrelated and so forth. So you've all seen rock, paper, scissors. This is, of course, the geologic version, which is rock, 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 which is igneous rock erodes to sedimentary. Never caught on. All right, the other thing we're going to talk a little bit about is deformed rocks. So we just introduced the concept of the sedimentary, metamorphic, and igneous rock types, and we're going to use that a lot in the next lecture, not so much today. We're also going to be talking about the deformation of rocks. So what they've done here is they have a box here, and they put a layer of sand and a layer of white sand and a layer of brown sand, a layer of white sand, and black sand in a box, right? So they're layers, like pancake layers. And then what they can do is they can squeeze, see that big shaft there? They squeeze it, and they can deform these nice flat layers of sand. And they deform into these complex folded geometries like we see here. Well, the same thing happens in nature, right? So these are deformed metamorphic rocks in this case. But you can see this looks a lot kind of like this, right? Okay, so rocks can be squeezed by plate tectonic forces and form folds like this, or they can break. And when they break, of course, that causes earthquakes. And they can break in any number of fashions. We'll talk about this next time. This is called a normal fault, for things are pulled apart. Here's a reverse fault where things are pushed together and they break and one piece moves up on top of another, or they move side by side with respect to each other. So these are different ways that rocks can break during a tectonic event. And here's an example of a fault that we see in a cliff face here, and a human for scale. We okay with all that?
Yes.
Okay, the third point before we get to the fun part of the class is geologic time. And the lesson that you should learn is that the Earth is really, 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 really old. All right. Now, this is a beautiful cartoon of geologic history, but it's cheating. Okay, so we got us up at the top there with looks like a rabbit with antlers and a man with a spade and so forth. And we have back here, we have the Earth forming 4.6 billion years ago. Okay, and here we have fossils coming in at around 540 million years ago. Okay, so they crammed like 4 billion years of Earth history into these two lower intervals, right? Because they're saying, well, nothing interesting is happening. There's not, animals evolving and plants evolving. So we're going to cram it. This is called the Precambrian down here. This is where I did my PhD. In fact, I was looking at these rocks about a week ago. All right. So, and again, this shows the different time periods. So we're up here at the top. And let's go on to the next slide. Okay, notice the time scrunched up, so we have 4 billion years down here, and that's just a lousy 500 million years, right? So a lot of time down here. This is unfair to the Precambrian, so we apologize for that. Let's see. And now if we look at that same time period in terms of fossil evolution, we can see the first fish from fossil evidence showed up around this period here. First land plants around 440 million. First amphibians 355 million years ago, long time ago. First dinosaurs around 200 million years ago. And of course, the famous loss of all the dinosaurs around 65 million years ago with the meteor impact. All right, so this is again the geologic time scale that we are dealing with. So back in the Archean, there was life forms, but it was just basically fossilized algae. It was a very primitive type of algae, and they formed very interesting structures. This is an algal occurrence in Western Australia, and it's very similar to what we see back in the Archean, but it's due to the unusual conditions that occur in this pond in Australia. Anyway, this was the smartest thing on the planet for like billions of years. So if we go to Mars or something and find a life form, chances are it's going to be something like this, some sort of cryptalgal mat. So up to like the first 4 billion years of life, this was about all we were seeing in terms of life. And then magically, around the start of the Phanerozoic, right around here, there are fossils in below this Cambrian explosion here, right down in here. But the problem is none of them have shells. So we can see them sometimes preserved, and they have very elaborate structures. But because they don't have shells, like trilobites have shells, they get preserved. So the big difference here between the Precambrian and the Cambrian and younger periods is that these things have shells and backbones and things like that, so we can actually find them more easily in the rock record. All right. By the way, you can buy these trilobites from Morocco for about $20 on eBay. So they're like this big, they're just gorgeous things. All right. Okay, so anyway, this beautiful cartoon here shows, the trilobites down here and some of the different, fish coming in, gigantic extinction at the end of the Permian. Here's the dinosaurs coming in, so on and so forth. Very neat figure. But in this class, we're really only going to talk about maybe the last 50 million years. I wanted to give you an idea of how great Earth history is. But in California, in Southern California, we're really only looking at around 30, 50 million years of history. So that seems like a long time, but compared to the history of the Earth, it's not. But we're going to jump back and forth in the millions of years like it was days on a calendar. But, so to put you in perspective, since the Eocene, here's the Eocene, this is the evolution of horses from the Eocene basically to the present. So you've all seen the evolution of horses, how they started off little and got bigger and bigger. All of that happened as we changed the geology of California. And just to put it in terms of man, all right, you're looking at the top. Lucy was 3.2 erectus, and then Homo anult I've added as of today. So all of the history of mankind has happened in the last 4 million years with the different related genus and species. Okay, so that was the last 4 million years, and we'll talk about that as well. All right, so that was all my little introductory presentation, and now we're going to get into the root of the class 20 minutes in. All right. Surface of the Earth. When you look at this picture, what do you see? Who said that? Good job. That's exactly the right answer. So you see a lot of blue colors and you see a lot of yellow colors. All right. There's two fundamental types of igneous rocks on the Earth crust. There's basically two types of rocks that you're seeing here. You're seeing the oceanic rocks and then the continental rocks, and that's the two different colors. Okay, oceanic rocks we can see on the island of Hawaii and some of the oceanic islands, and then this is from Yosemite Valley, again showing the sort of the continental types of rocks. If you look at them in sort of a cutaway view, we have this stuff called oceanic crust, and it's fundamentally different than continental crust. So there's two types of crust. One is oceanic, underlying the oceans. One's continental, underlying the continents. And they're very different. Now, the oceanic crust is made up of volcanic rocks. And that's this volcanic rock that's basalt. Okay, it's this black rock. If you cool basalt slow, this would be what it looks like on Hawaii. If you cool it slowly, it's called gabbro. So it's the same mineralogically. These are big crystals, those are little crystals. Density of basalt is about 3 grams per cubic centimeter. If you're on land, like on a continental margin, you see an andesite or a more granitic rock. There's a whole bunch of related rocks here: granites, granodiorites, diorites, tonalites. And anyway, we'll call this granodiorite here. So this is a typical igneous rock of the continent. So the typical igneous rock of the ocean basins, the blue color, is the basalts. The typical igneous rock of the continents are the granites, the granite family. All right? And it's a lighter rock, 2.7 grams per centimeter versus 3. Interestingly, you can stand right here and hold a hot dog and cook it on that lava flow. All right? When these guys go off, you want to be like 50 miles away. So there's a fundamental difference in the volcanic style of the Hawaiian type. Remember, we saw the houses burn up in Hawaii and so forth, but the guys are like standing there right next to their house burning up. When these type of volcanoes go off, you want to be miles and miles and miles away because they're very explosive. So there's two fundamental types of volcanoes. There's the oceanic ones and the more continental ones. So this is how a geologist would look at this, the different rock types, and they would plot the amount of silica or the amount of quartz in the system, which you'd measure by chemical analyses, and then here's the amount of minerals. So and you can see here's all the different igneous rock types. Again, basalt and gabbro. Basalt is the little crystals, gabbro is the big crystals. Here's granite versus rhyolite. Rhyolite's the tiny crystals, granite's the big crystals. So what you can do is you can do this, and all the oceanic crust in the world is made out of basalts and gabbros. In the continents, you can get anything from a basalt all the way through. So the continental volcanic rocks are much more complex than the oceanic ones. The oceanic rocks, again, are all basalts and gabbros, 95% or something like that. Whereas the continental, you can get a granite, you can get a granodiorite, you can get a diorite, you can even get a basalt. So it's a much more complex sort of system. But again, this is fundamentally telling you there's two types of crust. There's this oceanic crust, and then there's this continental crust. All right, so ocean basins are underlain by basalt and its coarse-grained equivalent gabbro. Continents are underlain by granitic rocks, this wide variety that we talked about. Okay, and then if you did this in cross-section, we see that continental crust tends to be thicker, and it's more granitic in composition. Here's the oceanic crust, it's thinner, and it's all basalts and gabbros. We also see words like mantle and lithosphere. In the olden days, we just talked about the crust, the mantle, and the core in terms of the parts of the Earth. But since plate tectonics evolved, we started talking about the lithosphere because this tends to be more what happens when the plates move. But we'll talk about that later. So we started off talking about the blue and the yellow colors being the oceanic crust versus the continental crust. But if you look deeper into the Earth, you see that there's this mantle and then this outer core and this inner core, and they have it all mapped out, and they tell you, what's going on. Composition. But on the one point you can say, oh, You know, the inner core is at, 5,100 kilometers to 6,370. You can sort of memorize those numbers. But then you can also ask the question, how the heck do you know that? Because there's no way you're going to drill a hole into the earth that's 6,000 kilometers deep, right? So how do they know what's going on inside the earth? Isn't that amazing that we know the inside of the earth, but we've never seen it? And the way we sort of suss it out is we can learn from earthquakes, and we'll talk about how earthquakes tell us about the center of the earth. From magnetism, all the compasses point towards north. No, they don't, and we'll talk about that. From meteors, we think that we can match the density of rocks here by comparing it to what meteors are flying by. And also, sometimes these rocks are found on the surface of the earth, which is really weird. How does a rock that's way down here get all the way up to the surface? It's very mind-boggling. But we'll talk about some of this. How could that be? Okay, we're back to this picture showing the Earth's surface. What else do we see? How about the pairing of Africa with South America? All right? So that's the theory. That starts with the theory of continental drift. History of plate tectonics. Plate tectonic theory had its beginnings in 1915 when this guy Alfred Wegener proposed his theory of continental drift. So he saw that South America fit into the armpit of Africa, but he also saw that there was fossils that shared the exact same distribution, and how could they have evolved separately at the exact same position if they weren't connected? All right, and of course then all these bizarre theories came up about these alligator guys swimming across the Atlantic and so on and so forth. And the thing is everybody saw this and you go, yeah, but how do you move a continent? I mean, continents are, they're huge and they're stuck to the mantle and the core. So it's not like you just, slip them apart like a rug. So everybody concluded that Wegener is a nice guy, though a bit nuts. Okay. Okay, and again, with continental drift, these continents are attached to all this stuff underneath, so how do you move it? It's kind of mind-boggling. They're very heavy. Okay, quiz. Other than the Atlantic Ocean, where else can you stick the continents back together? Siberia. Nothing jumps out at me. I'll show you another one later in the class that you'll go, oh yeah. You'll say, that's when I show you the other one, you'll go, oh yeah. I promise you. I'll probably forget to remind you when I show you, but all right. Here's a famous geology joke. You ready? Madagascar looks really much like the Caspian Sea. So in the early days of plate tectonics, when people would say, well, these things fit together, a guy would say, yeah, but Madagascar fits in the Caspian Sea. So now you're in on some of the real jokes in geology. Okay, let's go back to this picture. What are these enormous mountain ranges that we can't see because they're underwater? There's some sort of undersea mountain range, right? These are called mid-ocean ridges. Detailed bathymetric studies of the ocean basins reveal the presence of giant mountain ranges thousands of miles long. Look at how long this thing is. And about 1.5 miles high, 8,200 feet. So if there's no water and you live down here, you'd have to climb up 8,200 feet to get to the top of that, more than a mile. And what are the mid-ocean ridges made out of? Yay! All right. But what do they mean is the next question. But very good. They're made out of basalt. Okay. By the way, so this mid-ocean ridge is clearly in the middle. This one, not so much. So sometimes mid-ocean ridges aren't in the middle, which is kind of upsetting, right? We'll talk about that. Interlude, remnant magnetism. And you're like, oh my God, what's he talking about now? This is really weird, okay? Excited? Kind of nervous? All right, here we go. When mud particles, if you're in a lake and there's a mud particle that's washed in during a rainstorm, and that mud puddle is settling down to the bottom of the lake, or when lava freezes on Hawaii, the little magnetic minerals in the muds and the lavas tend to point towards north. And you can actually measure this. And we can, it's really weird. It not only points towards north, but it actually tells you what latitude you're at, because the magnetic lines vary as a function of latitude. So we can actually measure old lava flows and old sedimentary rocks, and we can tell you where the North Pole is and what latitude you're at commonly. Isn't that amazing? But what they found out around 100 or so years ago is sometimes the North Pole isn't in the North Pole magnetically, it's sometimes at the South Pole. There's flips of the magnetic North and South poles. So sometimes you'd be pointing towards the North Pole, other times you'd be pointing towards the South Pole. What causes this is they've argued about this in the literature, and they think it's some sort of happening of the molten core inside the Earth is moving around and bubbling and causing the magnetic field to change over time. But what we know is this happens, and it happens basically randomly over geologic time. So what you can do, and what they do is, here's your house in Irvine, and you have a cliff in your backyard. Here's this big cliff in your backyard. A geologist can shimmy up that cliff with his ladder, and he can pull out his magnetometer, and he can measure the magnetic declination of the rocks in that cliff face. And then he can tie them to other geologic, fossils and radiometric dates and so forth. And we actually have a magnetic stratigraphy, or a magnetic history of the Earth. So we can say at 27 million years ago, the North Pole was oriented at the South Pole. We know that sort of thing. All right? So this is the concept of remnant magnetism. Why are we talking about this? Well, what happened is, when they were studying these mid-ocean ridges, they pulled magnetometers on boats, and what they kept finding is the magnetic signals would keep flipping between north and south. Okay, so at this period of time, North Pole was in the North Pole. At this period of time, North Pole was in the South Pole in a magnetic sense. All right? So what they did is they saw this thing, and they called this striping, magnetic striping of the ocean floor. And this became this hugely important concept that they had no idea what caused it. So what they finally figured out is that all this is the new ocean crust, and this is old ocean crust. And what happens is a crack forms, hot magma comes up, and it freezes, and it orients with the magnetic north, if that's where magnetic north is, and then it freezes, and then it cracks open further, new stuff comes up, new magma comes up and freezes, and maybe the magnetic south is in the opposite direction, so you get a stripe in the opposite direction, and then the rock keeps cracking open, and new rock keeps freezing in between. So we're making new ocean crust in these mid-ocean ridges, and then it pulls apart like a conveyor belt, and this is older crust as we get out, and the striping is just telling you which way North Pole was, magnetic North Pole, whether it was towards the south or towards the north. Isn't that amazing?
Question.
Yes.
Is there a general concept of how many different flips there have been?
Yes, the question is how many flips in the magnetic polarity have there been? And I don't know exactly how many, but there's a ton.
Thank you.
All right. Okay, so let's try. I am going to now try a video.
Question from the back.
Oh, wait. Yes.
So as the thing is cracking and more molten stuff is coming up,
Yes.
does the circumference of the Earth get bigger?
Oh, you are so, what's the word I'm looking for? That's such a perspicacious, that's an excellent concept, and we're going to talk about it. That's called the expanding Earth hypothesis. All right, so here is a little movie showing how this works. So here you can see North Poles towards the north, and you've cracked open, say, South America and Africa, and you've got new crust being formed right down the center. Now we let it go on a little bit more. Now you see that North Pole jump to the other side. So now we're starting to make new crust that's in the opposite polarity, magnetic polarity. And then we keep going, and then eventually it's going to pop, and it goes in the opposite direction. All right? And then so think about it. This is where baby new crust is formed. This is how new ocean crust is formed. The age of this oceanic crust is 0, and it goes out equally in the other ages. So this would be teenage years, old people, like that. So this is all baby crust coming out. This is the formation of new oceanic crust, right? And this is how it's done. Whoop. Okay. Everybody get this? All right. Excuse me? Yeah.
Do we know why or how this switch happens?
They think it's some sort of, the question is, how does this happen and why does it happen? It's thought to be that the Earth's mantle underneath the crust is sort of like boiling oatmeal, and it's flowing and it's dragging things on top of it. So like when you boil water, and you might have or boiling oatmeal, you might have some crust that comes up and it moves around, and then it might get sucked back down later. We'll talk about that. All right, so so that was the first video. And then this one's even cooler. This is a guy from University of Chicago, Scotis, and he does these elaborate movies. This has been we have to see a commercial here, sorry.
What?
All right. Skip trail. He had to put on a soundtrack. Geologists have no life, so okay. All right, up to 2 minutes. Okay, so here is South America glued to Africa, and now the South Atlantic Ocean is opening up. See that? This is 130 million years ago. Now you've got a baby ocean basin here forming as the continents split apart. Now northern South America and Africa are still connected, but now we're forming the baby Atlantic Ocean, right? And now we're cracking South America away from Africa, and now we've got the Atlantic Ocean forming, the sort of Central Atlantic Ocean forming, and so on and so forth. So everything that you see here is an integration of all the geologic work that's ever been done. That's all this guy Scotis does, is he studies the plate tectonic evolution, and he makes these movies. So this is showing the evolution of the Atlantic Ocean relative to North America and South America. All right? How fast does mid-ocean ridge spreading occur? How fast do those plates move apart? It moves apart at about the same rate as your fingernails grow. So a couple of inches per year. So a couple of inches per year on a year basis isn't very much, but if you're over 100 million years, that is maybe 3,000 miles. Right? So, and remember the dinosaurs died 60 million years ago, so you can imagine that you could form an ocean basin about 2,000 miles wide since the dinosaurs died. Okay, here's some actual spreading rates from different mid-ocean ridges, and here, these are in centimeters per year, so, 5 centimeters per year, like this much a year, that sort of thing. I will show you. Okay, the question is, have we done a projection for another 200 million years out? People have. I don't have any with me, but I'll show you California I'll do a projection for California when we get a little bit further along. Okay, this is showing all the major mid-ocean ridges in the world, and I kind of like the fact that they used a baseball theme. But if you look at this, and you look at this and you go, oh yeah, here's the mid-Atlantic Ridge, East Pacific Rise, yeah. But then you look at it in a little bit more detail and you go, ooh, that's really weird. Baja California has one. So there's a spreading center in the Sea of Cortez. Isn't that weird? It just stops here. Why does this one just stop? Let's see. Iceland is right in the middle of a mid-ocean ridge. Isn't that weird? So you can go to Iceland and you're standing, you could put your legs on either side and one's going one way, one's going the other. Okay, oceans are underlain by basalt, continents are underlain by granitic rocks, a wide variety. And mid-ocean ridges, if you notice they're higher here and they're lower here, it turns out that they think that's purely due to the warmth. So you have hot magma coming up right in the center, and that's more buoyant. And they've done modeling, and they can show that it's basically a function of the fact that these are hotter rocks, so they tend to rise up higher than the colder rocks, which are denser. All right. So every time an airplane crosses the Atlantic Ocean, it's a little bit longer because of the seafloor spreading. Okay, now if you look at these, this is the mid-ocean ridge or the mid-Atlantic ridge. There's cross lines in it. See those cross lines? What are those? Here's a blow up. Here's two spreading centers here, and here's this cross line. These are called transform faults and fracture zones. So the idea is that in the spreading center, it's spreading apart that way. This one's spreading apart this way, but from here to here, it's actually moving against each other. You see that? So this is actually, you'll get little earthquakes there because this plate is moving that way and this plate's moving that way, and that's what's forming these fracture zones, and until they are both going in the same direction. So let's take a picture of this or check this out. These are all, so what I'm reviewing here is all the components of a normal plate tectonic system, and then we'll talk about Newport Beach in Southern California. So here's one spreading center, here's the other, and you can see that as they spread, they're actually moving against each other until they get past the ridge, and then they're spreading in the same direction. So is that making sense? So those are called transform faults. San Andreas is also a transform fault, but it's a weird one, and we'll talk about that later. And that's cheating to show you now. Okay, the young lady at the back suggested the seafloor is spreading. Does that mean the Earth is expanding? This is a popular hypothesis in the 60s by a small group of radicals that all these mid-ocean ridges were forming new crusts, so therefore the Earth was expanding like a balloon. But, trenches and subduction zones. So, oceanic crust is formed at mid-ocean ridges. Oceanic crust is destroyed at subduction zones. Subduction zones are enormous garbage disposals. All right? So what happens is oceanic crust gets heavier and denser, it gets colder, and it gets pushed underneath other geologic features such as continental margins. So this is called a subduction zone here. Okay, and what happens is the oceanic crust comes down here and eventually gets melted. So there's a balance between oceanic crustal creation at the mid-ocean ridges and the destruction of oceanic crust at the subduction zones. Oh, I want to go back and show you that. All right. This is a guy at a local college who does some great videos. Okay, I think I turned off the video. So anyway, here you can see subduction underneath the continental margin. Okay, so here's the oceanic crust going underneath this continental margin, and then it melts and it forms those andesitic volcanoes the very explosive ones that we talked about previously. So these might be the Andes Mountains in South America. So we have oceanic crust under thrusting, say, South America, and we have it melting before it becomes more messed up deeper, and we have it forming a volcanic belt there. Now you can also do what's called a volcanic arc. The subduction doesn't have to be underneath a continent. Here we have subduction, oceanic crust beneath another oceanic crust. So you can have oceanic crust being subducted under other oceanic crust. Okay, and the same thing happens is the rocks melt as it gets subducted, and it forms these volcanic arcs. So if you see a volcanic arc in your geographic studies, chances are it's associated with subduction zone. These are these trenches, these deep trenches that occur at the subduction zones. All right? All right, so here's what we have again. Here we have the oceanic crust being underthrust beneath continental crust in this case. We've got melting and formation of these andesitic, very explosive volcanoes that occur along the continental margin. We also have this trench, which is the deepest spots on the planet, like the famous Marianas Trench. Puerto Rico Trench is another one. And we have tons of earthquakes because you're taking this oceanic crust and you're pushing it down underneath, and you have phenomenally large earthquakes associated with it, like in Japan, for example. So here's where we see subduction zones. So this is the Nazca Plate, or the oceanic crust here, is being thrust underneath South America, and here's the Andes Mountains, which are the result of the subduction beneath the South American plate. So this is a subduction zone here, subduction zone here. Here we have a subduction zone associated with the Lesser Antilles in the Caribbean. Here the Atlantic Ocean is going underneath oceanic crust. So it's oceanic crust under oceanic crust. You have an island arc, which is the Caribbean, the Lesser Antilles, and so we have a subduction zone beneath oceanic crust. Tons of subduction zones in Europe. Who would have thunk? And of course, down in Indonesia, crazy tectonics going on. Okay, again, there's two types of subduction zones. You can have subduction underneath continental crust or underneath oceanic crust. Now what I've done is I flipped this over so this picture looks like that picture, right? But it's the same thing. So this is oceanic crust subducting beneath the continent. Here's oceanic crust subducting beneath more oceanic crust, another oceanic crust, but it's melting and forming this island arc. Okay, and here's it in cross section. Here you've had subduction underneath a continent, like in South America. Here you have subduction underneath an oceanic plate, like in the Caribbean. Is this all making sense? So this is all how the Earth works, and it's not what we're going to see in Newport Beach in Southern California. Yep?
Put it in perspective, please, to when I did a paper on Wegener in 1960-some, and it was still a theory. When did everybody go along with the continental Earth?
In the 60s and 70s. So the question is, when did plate tectonics become universally accepted? And the answer was, when I went to college in the early 70s, it was still argued a little bit, but by then it was universally accepted.
Thank you.
Okay, subduction zones. Identify continental arcs versus island arcs. So again, we said this is an example of a continental arc. This would be a continental where this plate is going underneath North America. Here we have the Lesser Antilles here, where you've got the Atlantic plate going underneath the Lesser Antilles. Here you've got the Cocos plate going under Central America. Is that continental crust? No, I think this is more this is more of an oceanic plate here. Anyway, so again, the subduction zones can occur beneath continents or beneath other oceanic crust, forming an island arc. And we talked about all this. Okay. Okay. Trenches are the garbage disposal. These subduction zones are the garbage disposals. It's where oceanic crust is destroyed. Nowhere on Earth is there oceanic crust older than 200 million years old. Okay, we know continental crust goes back to about 4.1 billion years. So in continental crust in Australia, some in Minnesota, we've got ages 3.8, 4, 4 billion years old. The oldest oceanic crust is only about 200 million years, indicating it's a pretty darn good, efficient removal of oceanic crust. Yep.
And speaking about oceanic crust always going, subducting below continental crust.
No, it can also go beneath oceanic crust. Yeah.
Can continental crust ever go below oceanic crust?
No.
The other direction?
No. But we'll get to the next. I'll get to the but in a few minutes. Okay. So continental crust cannot subduct, but it can do something else, and we'll talk about that. That's really cool. Okay, continental crust can do something really cool, but it's still normal. It's not weird yet. We're not getting into weird stuff. We will talk about weird stuff in this class. I'm just trying to build up the suspense, if you pardon me. Okay, again, associated with these subduction zones are volcanoes. So we have this ring of fire associated with all these subduction zones around the Pacific. You have volcanoes. So we don't have any volcanoes in Southern California, but if you go up into Northern California, Shasta, up into Mount St. Helens and so forth, those are all volcanoes associated with subduction zones. Okay, we used to have volcanoes here associated with subduction zones, but that's part of the story. That Sally knows, but her brother doesn't. Brother-in-law doesn't. Okay, again, so when you subduct oceanic crust, it partially melts and forms these volcanoes, either in the island arc situations or on the continental margins. Just talked about that. Do I need to talk about it? I'll skip that. How fast does subduction occur? Subduction occurs, again, about as fast as your fingernails grow. And here's some examples of subduction rates. Here's a fast one at 10 centimeters per year, but 6, 4, 3.5 centimeters per year, something like that. So subduction occurs about as fast as your fingernails grow. Okay, this is really important. When you have this is the universal sign, by the way, for subduction zones, When you go like that, I have subduction zone. When you push that hand under, you're kind of rumpling up your skin here, and there's tons of earthquakes associated with these subduction zones. Not only are there tons of earthquakes, but as you go away from the trench, they get deeper and deeper. So these red guys, the black earthquakes are shallow, 0 to 70 kilometers. The green earthquakes are from 70 to 300, and the red ones are deeper than 300 kilometers. Okay, so it goes black, green, red in terms of the depths of the earthquakes as that plate goes down. After about 700 kilometers, they think that the plate is getting so hot it's becoming mushy and it won't break as an earthquake anymore. So the deepest earthquakes on the planet are around 700 kilometers or so. Okay, so this would be a cross-section of Japan. Japan's an island arc. And here's the Pacific Ocean floor being thrust underneath, and here's all the earthquakes. And so there's a gigantic cluster of earthquakes that was named after a Caltech seismologist named Benioff. And this is called a Benioff zone, which is this linear geometry of earthquakes associated with the subduction zone. So Benioff discovered the earthquakes before they knew what plate tectonics was. He said, oh, look at this weird train of earthquakes going down, but they didn't realize it was because one plate was pushing down into the mantle below another one. You can also use complex imaging to actually show the geometry of these subducting plates. So this is showing a cross-section of that plate going down, using sort of like the same tomography imaging that you'd do your liver or something like that. Okay, now the next thing about subduction zones we need to understand for California is when this plate is pushing underneath that other plate, it's kind of like this one on top is kind of like a snow plow, and it scrapes up any goo that's on the plate as it goes down. So here's this ocean crust going down, and this thing is kind of acting like a snow plow or a razor blade, and it scrapes off a lot of the goo that's trying to go down. Okay? So this is called an accretionary wedge, and here's this plate going, subducting underneath this island arc here, and this is the goop that's scraped off like a snowplow or like a razor blade on your face. Oops. So here is the Lesser Antilles, the Caribbean. Here's Trinidad, Tobago. This is the island of Barbados that I worked for, I think, 6 summers on the island of Barbados. And if you look at the seafloor off Barbados, you can see it's all flat here, and then all of a sudden it gets rumply and glickly as you go in this direction. And Barbados is right at the crest of that. Well, what's happening is the Atlantic Ocean floor is subducting beneath the Lesser Antilles island arc, and this is all scraped up goo that's about 30 kilometers, 20 miles thick. So this is a snowplow. This is the snowplow. The Lesser Antilles arc is the snowplow, and it's piled up a pile of debris that's 20 miles thick. And Barbados is a little tiny piece that's sticking up above the air. Isn't that amazing? The reason it's so thick is they think it basically, there used to be a big delta coming off of South America here, and the snowplow just kind of picked up the entire delta that had poured out onto the seafloor and made this gigantic wedge of sediment, 20 miles thick. It's truly a remarkable thing. All right, so we now know the fundamental crustal rock types, basalts, andesites. We learned about the giant mid-ocean ridges. We also learned about chains of volcanoes along continental margins, the andesitic volcanoes, and at sea, the island arcs. Let's see what these things are. I'm running a little behind, as per normal. I'm going to skip this. All right, it's break time. Oh, that worked well. I was worried about losing half the class, so that's good.
One more second. Dad was with Texas
Our people love geology.
his whole career.
Let's hear it for geology.
And then Chevron bought him.
And I was with Chevron.
Yeah.
All right. So the world's crust, the surface of the earth, it consists of these tectonic plates. All plates must have boundaries. All ridges, transform faults, and subduction zones must end at a ridge transfer. Okay, so basically, every tectonic plate has to have on it either a spreading center, like a mid-ocean ridge, a subduction zone, or a transform fault. Every tectonic plate. So if we look at the Earth's major tectonic plates, we can see that these are the different tectonic plates that are moving with respect to one another. And this is a subduction zone, this would be a transform fault, this would be a spreading center. Every one of these plates has one of these associated types of features, either a subduction zone, a spreading center, or a transform fault like we see at the San Andreas that we'll talk about in horrendous detail soon. Okay, so those are tectonic plates, same thing, another picture. By the way, there's also things called mini plates. This is the major plates. There's also little tiny things, and we'll kind of talk about a mini plate today. Because the tectonic plates are moving with respect to each other, basically almost all the earthquakes in the world occur along plate boundaries. So that's one of the importance of plate tectonics is it really explains why there's earthquakes and where they are. Right? Now, in some cases, though, we see weird distribution of earthquakes away from the plate boundaries. But in general, you can see that we can define the tectonic plates based on earthquake locations. I wasn't going to tell you about this, but it's so cool, so I have to. How do you form a mountain? So where do we see mountains? We already talked about the mountains in the ocean. We can see that there's a mountain along a continental margin here. Here we have the mountains going inland a little bit. So we see them along continental margins here in Africa. They're over here. Some mountains here. So you can form mountains at mid-ocean ridges, but they're underwater mostly, except for at Iceland. We can form mountains by the subduction process. Here we have subduction. This would be like the Andes Mountains, right? So those are two ways of forming mountains, by mid-ocean ridge spreading and by subduction zones. But it gets better than that. Mid-ocean ridges are where the Earth is being pulled apart and the mountains form. Subduction zones are where plates are being pushed together and the mountains form. Mountains can be formed by collisions, the collision at plates. This is a different type of plate collision. Probably more painful. Consequences of collision. Here's two cars that ran into each other. And you can see that the cars got folded. Like, remember we talked about folding? And here you can see one car getting pushed underneath the other car. That's called thrusting. And also we see folding going on at the fenders there. And here we see an imbricate stack of cars. And these are all formed by collision. Okay, you can. The same thing happens during collisions in the Earth's crust. Here we see paired folding between that collision. Or here you can talk about collision by looking at your rugs. So we can see the slippage of the rug across this flat surface here. And as a geologist, when I look at rugs slipping like that, I start to do calculations of direction of slip. So mountains formed by collisions. The most glorious mountains in our planet are formed by collision of plates. There's several types of tectonic collisions. There's continental collisions, arc continent collisions, where an arc like Japan runs into a continent, or oceanic rock continental collisions, which I'll explain. So the most glorious one is when two continents bump into each other, and the most famous is the Himalayan mountains. It's very glorious. So the idea is the question was previously, what happens when you subduct a continental crust? Well, you can't. And in the case of the Himalayas, you tried to subduct continental crust under continental crust, and you formed the largest mountain belt in the world. Again, I'm running out of time, but I'll see if we can get a quick one up here. We might have to see another commercial. 58 seconds, we can do that. Oh yeah, this is showing the Indian, so here's Himalayas up here, and this is going to backtrack. So they're removing the spreading centers, so they're backing up India where it was prior to the formation of the Indian Ocean, and then they're going to put it back together, showing how India collides with Asia. Okay, come on, start it, doggone it. Okay, now they're going to go the opposite direction. And now India's moving north, and all of this brown stuff is going to be subducted by plate tectonic processes. Here comes India north. Here it comes, here it comes. Very exciting. These are probably island arcs out in front of it. And it's going to finally, so again, here's spreading centers going on, all this spreading going on. And finally, India collides with and forms the Himalayas. So that's pretty dramatic. So we've got other versions of this, but I'm going to skip ahead for time purposes. And again, we see this enormous mountain range associated with the collision of the two continents. We can also see collisions between an arc and a continent. All right, so the idea is that you have some continental margin here, you have a oceanic crust here, and here comes this arc, and then it slams into the continental margin. It tries to subduct the continental margin, and it's basically like plugs up your toilet. It can't go down. The continental crust can't go down, and it dramatically changes the nature of the tectonic boundary there. So where do you see this? Well, in the Caribbean. Here's Cuba. Cuba was an island arc that ran into the Bahamas. And if you do a cross section through Cuba, here's Cuba here, and here is the Bahamas here, and here's this zone of crushing that occurs between Cuba and the Bahamas. Isn't that amazing? And you know who made this picture? oil guys. They were trying to figure out if this smash zone would have trapped oil in here. So if you look here, there's a mention of reservoir presence and seal presence. So they're saying, should we drill here to see if we can find oil? Taiwan is one of the coolest places in the world geologically. Not only are they politically an affront to China, but they're also geologically an affront to China. Taiwan is an island complex that is trying to thrust over China. All right? So interestingly, and it's happening right now today. You know, like Cuba already happened millions of years ago and it's kind of stuck there. Taiwan's actively trying to overthrust China today. So if you start down here, this is called the Luzon Island Arc, you see what looks like a normal subduction zone with this Luzon Arc thrusting over the South China Sea. It looks like a standard subduction zone. But as you go north, you see that this island arc is now trying to thrust over the continental crust of China. And the reason it's like this is it's kind of like thrusting obliquely. It's like a triangle closing up. So here we have Taiwan thrusting over China, whereas down here in the Philippines, it's just like a normal subduction zone over oceanic crust. But the point is Taiwan is involved in an arc-continent collision, and as a result, it's pretty mountainous in Taiwan. This is a picture of Taiwan showing you some of the uplifted rocks. So subduction zones occur when you subduct oceanic crust. We already learned this, but we're going to put a twist on it. A lot of oceanic crust doesn't look like this, but it looks like this. It's thick oceanic crust. What happens when big old thick oceanic crust goes into a subduction zone? We know we can subduct this nice thin crust. What happens when you subduct something like Hawaii that's much thicker? Well, the same thing happens. It sort of plugs up the subduction zone. So here we have an example of an oceanic plateau that's trying to be subducted under an island arc, and it basically plugs up. See the subduction zone clogged from this anomalously thick ocean crust. So these are all different ways of forming mountain belts. And that's why I'm talking about this. So now, in this hour that I've been speaking, I said that you can make new oceanic crust at mid-ocean ridges, right? And you can destroy oceanic crust at subduction zones. How do you form continental crust? Isn't that weird? So we know how to make oceanic crust. We know how to destroy the oceanic crust. How do you make continental crust? Well, the answer is you make continental crust through collisions. Either by continent-continent collisions, you make a bigger continent because you had two continents and they came together and made a bigger one. Or if an arc slams into a continent, that becomes part of the continent. All right? How do you destroy continental crust? You basically can't. So that's why we have rocks that are in continental crust that are pushing 4 billion years old or around that age. Right? Okay, so we talked about, we said we can make mountains by mid-ocean ridge spreading, by subduction zones, by collisions. Oddly enough, you can also make mountains by pulling things apart. Isn't that weird? So this is the mountains of Nevada. Nevada has a bunch of mountains in it. You can see they look like caterpillars crawling north. And it's all formed by pulling the earth apart, what we call extensional tectonism. So what happens is you take the crust and you pull it apart, and some of the blocks go down and others go up relatively. All right? And so the nature of these breaks in the rock, these breaks in the rock are of course called faults. They can have different geometries. And this one key geometry that they've only discovered about 20 or 30 years ago are these, when it pulls apart, it may have these sloping geometries like that. And this turns out to be very important for our next lecture. So these are called detachment faults, but we'll talk about these later. But again, what you're doing is you're forming significant topography, like mountains, by pulling things apart, which doesn't seem to be logical to me, but I'll accept it. All right. So again, you can either squeeze the earth together and fold it and make mountains, or you can pull the earth apart and it can form mountains as well. Deformed rocks, folding in rugs and rocks. So these are folded rocks. Anticlines mean the layers dip away from each other. Syncline mean they dip towards each other. Anticlines and synclines. Here's an anticline and a syncline in a rug. And then here's a result of an earthquake where we have a fault displacement. And here's a cross-section of this fault where the rocks have broken and moved apart. I'm going to skip that. So anyway, the cool thing about the consequences of mountain building is it makes beautiful scenery. So I'll just go through this kind of quickly. Look at the scale here. This is like tens of miles across. This is on the scale of a highway cut. This is on the scale of something that's the size of your fist or something. So lots of different geometries associated with deformation, plate tectonic deformation. Oh, we'll see prettier ones than that. All right. This is in the Alps, I think. That's a beauty. And then, so these are again folding. This is folding where you're bending the rocks. And then faulting is when you're breaking the rocks and you're splitting the rocks like this. And notice in this fault here, this layer got offset from that layer and so on and so forth. Okay, we'll skip that. Everything we've talked about so far is normal geology. It was pretty dramatic, right? We saw giant mountains and ocean basins and subduction and volcanoes. All of that is normal. And it's not like what we're seeing here. So define normal. As I said, we'll be talking about the amazing, incredible, unbelievable geologic history of Newport Beach in Southern California compared to what? Compared to what's normal. So mid-ocean ridges are normal. Subduction zones are normal. Transform faults are normal. Continental and other collisions are normal. Even collisions are normal, all right? So somehow the geology of Newport Beach in Southern California is different than this normal craziness. Let's get crazy. Okay, let's now that we have a basic feeling for plate tectonics, we know about how the plates move and their size and geometry and so forth. Now we can say, let's look at California in detail. All right, we haven't done that yet. So here's California, and we all know about the San Andreas Fault, and it's somehow tied to this subduction zone. This is Mendocino right here, beautiful place to visit. And north of Mendocino, there's a subduction zone with volcanoes onshore and so forth, Mount St. Helens and so forth. And if you go south of like Baja here, you have a subduction of the Cocos Plate underneath Central America. So this is, here's Mendocino here. Again, this looks pretty normal. This is a subduction zone under the North American Plate. It's normal, right? In Northern California, Oregon, and Washington, looks normal. Okay, and here's a nice cutaway view. Here's Washington, Canada. Here's all these volcanoes. Here's the subduction zone. There's a little spreading center offshore that makes the Juan de Fuca Plate. Looks normal, no problem. Then we go, so north of California is normal. So we looked at all those cutaway figures. Again, there's the subducting plate north of in Washington, Oregon, and it's forming those volcanoes like Cascade volcanoes. So everything in north of Mendocino seems to be pretty normal. We all okay with that? Okay. Again, another beautiful figure. Okay, now south of California, everything looks pretty normal. So here we have Mexico. Here's a subduction zone. Here's a plate going underneath it. There's volcanoes here. Again, this looks like a normal subduction zone, right? Do you think I'm taking you somewhere? You're excited about the... All right. So what about California? So to sum up, Northern California and north of there seems to be a routine subduction zone with a continental arc, and the Cocos Plate area seems to be the same in the south. So we've explained everything south of California and north of California. What about California? So this woman here is named Tanya Atwater. And if you guys were geologists, I wouldn't have to say this woman here is Tanya Atwater, because she is arguably the most famous woman geologist, geophysicist in the world, maybe ever. Yay for Tanya. And the question is why? It's because of Tanya's theory. Again, every geologist in the world knows Tanya's theories. Isn't that amazing? Here's Tanya's theory. This was proposed in, I think, the late 60s. In the olden days, before there was a San Andreas Fault, the continental margin of North America, including Los Angeles, there's Los Angeles, looked like Peru. There was a big oceanic trench going the entire length of North America, and there was island arc system, which is now known as the Sierra Nevada. That was an active island arc system, and it just looked like Peru. But what happened is around 20 million years ago, 30 million years ago, when the horses were evolving, we subducted a ridge, a mid-ocean ridge, this Pacific plate. And what happened is, as it subducted, it changed the geometry of all the motion. So instead of having this going on where we had the Pacific plate subducting under North America, because of this spreading system that was going under, it changed the geometry and the vector motions and so on and so forth. And that's what formed the San Andreas Fault. So Tanya's original theory back in the late 60s was how the San Andreas Fault formed. Okay? And she was immediately recognized as, oh, you are a goddess. All right. So when I was in college in the early 70s, Tanya Atwater was, oh yeah, everybody knows who she is. And she was probably like, 30 at that point. Okay, and as this spreading center continues to subduct, the San Andreas Fault is growing further and further. It's becoming longer and longer with time. So right now, the San Andreas Fault ends at M, which is Mendocino. Okay, and it goes down to Baja California. So at about 5 million years ago, Baja California separates from Mexico. Remember, there's a spreading center in Baja California. It's got a mid-ocean ridge. So little Baja California, there's a spreading center, a mid-ocean ridge behind Baja California. And if you look, Baja fits right into that part of Mexico. So remember, we were looking for pieces that fit together of the continents. Well, Baja fits right into Mexico. All right, let's see. Collision and subduction of mid-ocean ridge in North America about 20 million years ago in Los Angeles. It started in Los Angeles, as everything does, it seems. San Andreas Fault is a result of the subduction of a mid-ocean ridge. The end of the San Andreas Fault is about the location of Mendocino. No Baja California, Gulf of Mexico until about 5 million years ago. So only 5 million years ago to a geologist is like, 10 minutes ago, right? And so that's very young origin of Baja California. Gulf of California is a mini ocean basin with a central ridge. Okay, let's see what this here video is. This is one of Tanya's animations. In her older age, I think, this is one of Tanya's. Okay, let me stop it. So this is geologic time here, going from 40 million years to about 0 million years. And you can see here's Los Angeles, here's the Great Valley here, here's Nevada. Nevada is going to get pulled apart. Remember, the extensional faulting in Nevada makes the mountain ranges. So that's why Nevada's so skinny right here. Here's Baja California is going to form here. So LA is right about down here where this mid-ocean ridge is going to hit around 30 million years ago. Are we all on board? Okay. So this is by this animation you're seeing was made by Tanya about 10 or 20 years ago. and it's been downloaded. So now we've subducted the mid-ocean ridge here, and now we're starting to form the San Andreas Fault in this position. All right. And now you'll see, now here's, you can see the San Andreas Fault forming from that subduction of that ridge. Okay. Okay, now notice that the San Andreas Fault's moving north as this transform fault becomes subducted. So the length of the San Andreas Fault, right there. Now, the San Andreas Fault at around 20 million years is offshore of sort of Bakersfield, maybe. So this is Bakersfield here, maybe a little north of Bakersfield, Fresno. See that? Baja California is still connected to Mexico. Okay, now, by the way, now watch Nevada starting to pull apart. See that? Okay, here again is San Andreas continuing to grow. We're at about 17 million years. Okay, see Nevada growing, and here's the San Andreas continuing its northward march. Here's Baja still connected to Mexico. All right, now California is starting to take shape. Here's Nevada looking pretty much normal. San Andreas, it's about where it's going to end up. And now we're starting to see Baja pull apart. Oop, what happened? Okay, and we're up at around 4 million years. Here's that spreading center associated with Baja California. Here's now the San Andreas Fault going up to Mendocino, and that takes us up to about the present. All right, so that's the geologic history that Tanya came up with. So that's we just looked at this. And here's another view, and here is Baja Peninsula here. And if you undo this mid-ocean ridge here, you see that it connects right up into Mexico. Just like Africa fits right into the armpit of South America fits into the armpit of Africa. Okay, the San Andreas Fault. So the San Andreas Fault was formed by the subduction of a mid-ocean ridge. It's also called a transform fault, but it's very different from the ones we looked at separating different segments of the mid-ocean ridges. Isn't that crazy? Before the San Andreas Fault, the coastline of North America looked like South America or the coastline of north of Mendocino. The Sierra Nevada granitic rocks are the uplifted roots of a continental volcanic arc such as that is currently present in Washington, like Mount St. Helens and in the Andes. So is this what we mean by the amazing, incredible, unbelievable geologic history of Newport Beach in Southern California? Not even close. This is interesting, but it's going to get crazier. Okay, remember this remnant magnetism? Remember, that's how we could tell the North Pole versus the South Pole? Well, here's what happened in California. This guy, Bruce Leyendijk, Tanya Atwater taught her whole career at UC Santa Barbara. Bruce Leyendijk also taught at UC Santa Barbara. Bruce Leyendijk studies paleomagnetism. So he would go out and measure magnetism in rocks. And he was studying the Channel Islands off Santa Barbara. So that's where their university is. And he went and he studied the paleomagnetism of the Channel Islands. All right? And what he found was the little remnant, remember the little mud particles follow and they point towards north? Well, they didn't point towards the North Pole or towards the South Pole. They pointed towards the East Pole. All right? So for like a decade, they're like, he would say, and the rocks in the Channel Islands Park point towards the East Pole. And people would like, you're nuts or something, right? So, Bruce Leyendijk is professor of paleomagnetism at UC Santa Barbara, same place as Tanya taught. He studied the paleomagnetics of Cenozoic rocks on the Channel Islands offshore of Santa Barbara, and in 1985 noted for the rocks he studied that north direction was rotated 90 degrees. How can islands rotate 90 degrees? And there's all these papers about, the San Andreas rotates them like marbles and things like that. So at any rate, Tanya made a movie about this, and this is the movie, and this movie is the basis of our class. So we're going to interpret everything, well, most everything, in terms of this movie. You ready?
Yes.
So, according to Tanya, we start off here. We're at, let's see, it's hard to read at the top. What's that, 20 million years ago? Okay, so remember, around 20 million years ago, we started to subduct that mid-ocean ridge from our other movie. So here's a little remnant of that mid-ocean ridge. Okay, notice here's Santa Barbara there. It's rotated around. Here's San Diego. So in this reconstruction, you could have driven from Santa Barbara to San Diego about the same distance it is from San Clemente to Oceanside or something like that. Okay? All right, so what's happening is during the early evolution of the San Andreas Fault, Santa Barbara is a block that rips off away from San Diego, here's Santa Barbara, and rotates. Guess how many degrees it's going to rotate? Hey, you guys are sharp. Okay, so here it is rotating like that. There's Santa Barbara. Here's San Francisco up here. Okay, and then eventually it's going to rotate and sort of slam into Santa Maria at the present time right there. So this was Tanya's explanation of how Bruce Leyendijk's paleomagnetism was off by 90 degrees. It's because there's this thing called the Santa Barbara block, and the Santa Barbara block ripped off during the evolution of the San Andreas Fault and rotated 90 degrees associated with that rotation. And that's what we're going to talk about in lots of detail. All right, let's think about this. That little rotating feature, the transverse ranges, also known as the Santa Barbara block, is actually tens of square miles. It's a big thing. I don't know if it's 100 square miles, but it's pretty big. When it rotates, what happens to the Earth? I mean, you know, she's got this little cartoon, and you guys are like, yeah, it's rotating around. It's going to be 90 degrees. But what does that mean? I mean, this thing is huge. It's tens of square miles, maybe, I don't know, 100 square miles. It's a gigantic block of rock rotating. And it's attached to, you know, the mantle of the Earth and stuff. What's going to happen? Well, one of the things that happens is as this thing rotates around, it forms a hole behind it. And that hole is the Los Angeles Basin. So the reason we have a Los Angeles Basin is associated with the rotation of the Santa Barbara block. The island of Catalina, we'll talk about in some detail next time, is the rocks that we see on Catalina are really weird rocks. They're bizarre rocks, and we'll talk about it next time. But the reason we see them on Catalina is because of the rotation of the Santa Barbara block. So, yes?
The harbor between Catalina and San Clemente, or what, Dana Point, I think is the deepest ridge, I want to say, in the world.
Probably not.
It's 4,000 feet deep.
Oh, no. That's the water depth between Catalina and San Clemente.
So doesn't that have to do with?
That's actually, no, it's a little bit, but not really.
Okay.
I think it's a later effect. It's a vertical, I don't want to go into details.
Okay.
There's something weird happening there, but the water depth is not that unusual. Any other, yes?
So, make sure I forgot this. When the professor was at the Channel Islands
Yeah,
and discovered the 90-degree rotation,
yeah.
it wasn't really the islands, but it was Santa Barbara block?
Well, the islands are part of the Santa Barbara block.
Gotcha.
All right. So they're just the subaerial exposure of that gigantic block. And they've actually gone in and measured paleomagnetism all around there to try to figure out the limits of that Santa Barbara block. I want to check one thing here. Yeah. All right. Oh, God, I ended it. Sorry. I'm building up to the conclusion. Let's see. End. Where's end? I'll get there in a sec. Sorry. Okay, so summary at this point. We define normal geology as characterizing mid-ocean ridges, subduction zones, transform faults, and collisions. California has a transform fault, the San Andreas, but much of what we see in Southern California is a result of the migration of the Santa Barbara Block from its initial position of Newport Beach. And the Santa Barbara Block I tied it into Newport Beach and Laguna, or San Diego or whoever, to where it slams into the coastline near Santa Maria. So this is the weird history that we're going to focus on in this class. So I am a little early, but this is basically the start of the class. So what we're going to do is we talked about the plate tectonic history of Southern California now, and the next class I'm going to talk about the rocks that give you a little bit more color and texture about what happened over the last 30 million years. So we're going to talk about that same history that Tanya defined in her animations, but now we're going to focus in on looking at what the rocks did. And the rocks are very unusual, and the cool thing is you can actually visit them. Like I could take you on a field trip and you could touch them and poke them. So for example, we'll look at Dana Point Harbor and places like that. And then on the third class, we'll talk about earthquakes in Southern California. That's not my specialty, but it's interesting that the Tanya Atwater model also sort of explains the earthquakes that we see in the area. So we'll talk about that. And we'll talk about the Long Beach earthquake, which is a big earthquake in this area. And then on the fourth class, this is a little bit on what happens in the ice ages in our neighborhood. So that's all I've got for today. Do you have any questions? Yep.
We went up to the San Andreas last winter, and she was telling us that if something happened, I can't remember quite exactly what it is, the east part would separate from the west part, and we would be separated from the continent. Do you know about that?
The question is what happens in the future along the San Andreas Fault? And next time I'll show some different pre-constructions on what's going to happen in the future.
Because we wouldn't be able to, we would have to be shipped. We would not be.
One of the simple ideas is that we're moving north with respect to, say, Las Vegas. But there's more complexities associated with that. Normally we just say, oh, we're going to end up, thrusting under Alaska eventually. But that's pretty much oversimplified. Yes?
South Bay, Los Angeles South Bay, eventually will fall into the ocean.
Yes, we're all going to die. Is the South Bay going to fall into the ocean? Is the South Bay, we're going to be flooded during the with the climate change. I don't know what's going to happen to the South Bay.
Because on the map,
Yes.
San Diego is more inland.
And
Actually, right now it's going to sea.
yeah. But there's no new block rotations going on. So you'd need a new block rotation if you wanted to switch around. So I'm not sure.
Question over here?
Yeah, yep. Oh, you got a microphone too. You have the power.
Makes me really important. You talk about the transverse ranges being associated with this Santa Barbara block.
Yeah.
Are the Santa Anas involved in that in any way?
The Santa Anas.
The mountains up here behind us.
Oh, well,
It's a small
let's
range.
see. We'll talk Santa Ana. No, those are part of the strike slip system. When I was in college, they always used to say, one of my professors used to say, we used to marvel that the transverse range was one of the only mountain ranges that's basically perpendicular to a continental margin. All the other mountains are parallel to the continental margin. And now we know it's because it's been rotated from the block rotation. The Santa Anas and the San Gabriel Mountains, I'm at a loss.
Okay, thank you.
Yep.
In the Mid-Atlantic Ridge,
Yeah.
the crust is spreading, that allows material to come up.
Yep.
But in the middle of the Pacific, the Hawaiian Islands, material is coming up, yet there's no fault.
Good.
So
So
what's-
the question is is Hawaii part of a mid-ocean ridge system? And it's not. One of the theories of Hawaii is it's associated with what's called a hot spot. And the idea is that the Pacific plate is moving, and there's this really hot spot that's forming a volcano. And what happens is, as the volcanoes pop up, and then the plate will move a little bit, then the volcanoes cool and they fall down. So you have this chain of islands in a line oriented, I think, northwest. And they become older. Hawaii is the youngest, and they become older towards Kauai, towards the northwest. And the idea is it's a hot spot, and the plate is moving over, and you're just seeing older volcanoes on one end and younger volcanoes on the other. So it's not a mid-ocean ridge system.
Any other hot spots?
Yes, there are. In fact, one of the theories, by the way, so I used to be a professor, and I used to do a lot of plate tectonic studies. And then I went into the oil industry for 25 years, and then I became very detailed about oil stuff. And so some of this is dredging up memories from long ago. But as I recall, Yellowstone is thought to be a subducted hotspot. So the idea is that one of the theories of Yellowstone, where all the geysers are and everything, is that there is a hot spot, and the oceanic and the continental plate, it basically got subducted, and it formed the Columbia River basalts in Washington, and now is underneath Yellowstone. So there are other hot spots. They are very important for the plate tectonic guys to monitor motions of the plates and so forth. So I don't know them all, though. It's out of my realm. Yep.
So Hawaii is getting bigger each year because the hot spot keep
Yeah.
having the eruption.
Yep.
So is any other part of the island, Hawaii Islands, any of them will have less of the land?
So again, the big island, Hawaii, is really in the center of the hot spot. As far as I know, none of the other islands are volcanic. So that means they're away from the volcanoes. And what happens with cold oceanic crust is it tends to subside with time. So in general, these islands will be moving downward as opposed to upward. Okay. By the way, one of the big challenges in global climate change is, they always talk about sea level rise, but accompanying sea level rise is land subsidence. So when you're doing a sea level rise study, you have to subtract off the impact of land subsidence. So for example, in the Mississippi Gulf area, a lot of that is a big, where the Mississippi River comes out in Louisiana and so forth. That's a big pile of mud. And the mud compacts with time. So when they do the subsidence studies, they have to say, well, part of it's due to sea level rising from the melting glaciers, but also part of it's due to the fact that you're compacting mud. So the Earth is a dynamic place, and we have to do these calculations. And the same thing would apply to Hawaii, where as you go off the main island. Yep.
Island that is growing, is it growing only from volcano, or is it also growing from collision?
No, it's at a mid-ocean ridge. So Iceland is in the position of a mid-ocean ridge. They're very proud of it. It's kind of unique to be on a mid-ocean ridge. Yeah, 1 foot on each plate, yeah. And, but it's growing only from, one of the arguments about Iceland, though, is why is it above sea level, whereas the rest of the mid-ocean ridge is, miles below sea level. And I can't, maybe there's a hot spot there, I don't know, kind of similar to Hawaii at Iceland. But I really don't know, it's not in my field. But at any rate, no, there is no collision associated with Iceland. It's a mid-ocean ridge spreading center. And why is it higher? I can't remember. Age-related.
I understand that when they decided to put the nuclear plant at San Onofre, they weren't aware of the fault lines that were lying below it. And are those dangerous? Are they subduction? Are they slip fault lines? Is it something additional we have to worry about?
So one of my old professors used to say that the way you could map active fault zones was to look for schools and hospitals. The irony being that they always seem to put the schools and hospitals in the worst possible place. I have not studied the faulting. I've heard about the faulting at San Onofre, but I don't know. If chances are, if it's San Onofre, then you would assume it's San Andreas type related. But there's a lot of different fault systems. There's the big. We'll be talking a lot about the faults around here, and the big one is the Newport Inglewood fault, which is offshore of Huntington Beach, and that's where the Long Beach earthquake was. But anyway, we'll talk about that the next 2 lectures. But I don't. I'll try to look up for San Onofre. Any other questions?
Okay. Thank you.